shall we start? Right, so now we have, I have saved it under different name. So we have this, if I ask it to show all, we have this particular structure and it has a rough foundation. And we are going to consider that we are having clay soils and the soil conditions also can be variable. So we can have some few pockets with different properties as well. So what's the way that we can do the modeling? So to represent soil, it is not enough to represent the soil directly under the rough foundation. We have to represent the soil in beyond the building as well. So what we do is we'll go to the grid and ask it to modify. So we'll consider a grid beyond this point. So EF G, and we'll go for minus 7.5 and plus 37.5. And copy this through. And this way also 6 and 7 at minus 6 and 30. So now you can see we can model beyond the structure as well. And I will actually consider a little more. So what I do is I will go for modify F D H as minus 15. J as 45. This way also I will consider 6, 7, 8 and 9 and minus 12 and 36. Okay. So you can see now we can model soil in this area as well. So what I do is here you can see I will select all these and move the structure away so that I can do the modeling of the soil independently. So what I do is I'll ask it to replicate the structure at a height of 10 meters, and in doing so I'll ask it to delete the original objects as well. So now the structure is away from the foundation area, which will allow me to model the foundation, the soil, without worrying about the structure. So structure is connected to the raft foundation, and the thickness of the raft, we see the thickness of the raft. Earlier we saw that 1.5 meter thickness may be too much, so we'll modify it to 1200, or we can make it yeah, we'll keep it 1200 for the time being, and we'll make it 1.2 and 2. Say okay, and now we have to define the soil. If you are going to model the soil, we have to first define soil. So I'll define two soils. So add a new material. Material has properties of other, and the material is soil 1. And you can see to define soil, we need the Poisson's ratio and the modulus of elasticity. And to find the modulus of elasticity of clay soils, you can refer to the last note, where we looked at the modulus of subgrade reaction of clay soils. And we said the undrained cohesion is equal to 4.5 times the SPT number. So if you are going to have a raft foundation for a 8-story building, then you cannot be having very weak soil. You should be having reasonably strong soil. So let's consider that, you know, we are having something like laterite soil, which allow us to go for a raft foundation, and the water table is say about 1 or 2 meters below the existing ground level. So we are going to consider that this laterite soil will behave as a clay soil primarily, and so it's the undrained cohesion. If we get a SPT value of like 12, SPT value like 12, so we are going to consider that the SPT value is 12 in the soil. So it's a reasonably strong soil, and undrained cohesion is 4.5 times N, which means 4.5 into 12. Cu is equal to 4.5 times N, which gives 4.5 into 12, and the value is 4.5 into 12 is 54. So undrained cohesion is about 54, and then to find the subgrade reaction, which is a function of elastic modulus, there is an equation, a relationship between ES and undrained cohesion. And so generally these laterite soils, which are of which are residual soil, the over consolidation ratio may be about 1.5. So we can say that, you know, over consolidation ratio is less than 3. So we'll have OCR less than 3, and we know laterite soil is a good soil. The plasticity index will be less than 30. So we are going to get this relationship, the ratio as 600. So the elastic modulus of laterite soil will be Cu multiplied by 600. Cu is 54. 54 multiplied by 600 is 32,400. 32,400 kilonewtons per meter square. So the elastic modulus of soil, which is a reasonably good soil within the water table, the elastic modulus will be something like 32,400. 32,400. So generally, you know, we will not go for very high elastic modulus. Generally, the elastic modulus may have a upper bound of around 40,000 to 50,000 kilonewtons per meter square. But in our case, you know, we are getting an answer of 32,400 kilonewtons per meter square for the elastic modulus. Is that clear to you? Aruna? Tamira?
Yes, yes, sir, it's clear.
Yeah, okay. So now we are having a soil. Yeah, thank you. So we can say the elastic modulus of steel is 200 into 10 to the power 6, and concrete something like 25, 27 to the power 6. Whereas in this case, for soil we are getting a very low value, 32,400. So that is the value for elastic modulus of soil, and the Poisson's ratio for soil is generally around 0.3 to 0.4. So we'll keep 0.3, and the unit weight is only 18. So generally the weight of soil would be around 18 kilonewtons per meter cubed. So we keep those values, and if you want, you can switch to the advanced property display as well. The advantage of that is you can actually laterite soil 1, and we say that other, and here you can see earlier we could actually allocate a value for weight per unit volume, and this has to be 32,400, and Poisson's ratio is 0.3. And here, if you want, you can actually see what I'm going to deal with the soil, because now we are modeling the soil and structure all together. It may be a good idea that we make the mass of soil 0, because we don't want any contribution to the natural period of vibration from the mass of soil. So otherwise, the mass of soil will also be considered when it calculates the natural period of vibration. So by going with advanced properties, we can actually change the mass of the soil to almost 0, whereas the weight can be kept with the model, so that we'll be able to see how the variation of how the weight of the soil also contribute to increasing stress as it goes down. So we'll go with advanced properties, and the type of soil is laterite soil 1, and we'll add a copy of the material that is laterite soil 2, or we can say clay, and let's say that clay soil 1, and let's say there is a pocket of clay soil where the SPT value has dropped to about 8. SPT value has dropped to about 8, and so if the SPT value has dropped to about 8, then again we have to see what's the value of elastic modulus. So it becomes 8 into 4.5, that is the underlying cohesion 36, and then we have to see the elastic modulus, and it's a pocket of clay. So still we'll consider the over-consolidation ratio is less than 3, and we have a weak pocket, but we go with 300. There's a chance that the plasticity index can be close to 30 or even more than 30. So we'll go with 300, and then you get elastic modulus of 10,800. So just to demonstrate, we'll consider that there's a weak pocket of soil where we have to go with the elastic modulus of 10,800, and so we just consider it that way. And so we are having two types of soil: the laterite soil 1 and clay soil 1. Laterite soil 1 and clay soil 1. So the next question is, how are we going to define the soil properties? And we are going to define the soil properties by using solid elements. So we can add laterite soil 1 and it is laterite soil 1, the soil type 1 is laterite soil 1, and here we have to consider what is meant by this incompatible mods. And incompatible mods is an option given in the program to take account of bending effects when the modeling is done with solid elements, because solid elements are not capable of actually capturing the bending effects. But an option is given in sap2000 where the bending effects can be captured. So, but soil is not capable of taking any bending moments. Soil can take only compression. So because of that reason, we have to switch off this incompatible mode option. We have to switch off this incompatible mode option. which means, now we are considering that it is not carrying any bending effects are not transferred between the elements. It's only the deformations that are transferred. So we have to turn off this incompatible mode option, and we can define the laterite soil 1, and we can also say clay soil 1, and the soil is clay soil. And so now we have two different types of soils. And then what we can do is, we'll look at it. Now I'm going to create the soil profiles. And to create the soil profile, what I do is I'll go to Z0. Not Z0. And what I can do is I can select any element. I'll just select ground floor 200 from here to. So now I have the starting point of defining the soil. So you can see this structure is now at a high elevation at this level, 0 level. I have this one. Let's clear the clear selection. And what I do is I select all this, and as I have done earlier, I'll divide the areas in the same ratio of 6/6, so that these elements and these elements will all tally. So those elements will tally. For example, here you get 0, 0, 0, and then next element is, here you can see the dimensions, 1.250, 2.50, and 2.51, 2.52, and so on. And if you look at this location, D00, 1.25, sorry, 00, not 00, 7.5, what is this? D00, at this location is 1.250, 2.50, 2.51, 2.52, which means the grid here and grid here are the same grid, the same. And so now I can extrude this and convert it to the soil. But before doing that, what I do is, I will make this, now the structure is only this area, and I am having a massive area of soil. So just to keep the weight of the model lower, I will remove 3 lines here. Now I'll remove 3 lines here. I'll remove 3 lines from here. And I'll remove 3 lines from here. This is done just to keep the size of the model to a reasonable level. And if I just look at 3D, here you can see the structures here. The soil is surrounded in a larger area. And the rough foundation is in this area. One grid beyond the building is rough foundation, and the rest of the area is all soil. So rest of the area is soil. So again, I will go for Z0 view. And what I do is, I'm going to extrude this. Extrude this. Extrude. Areas to solids. Laterite soil 1. Laterite soil 1 is the type of element that I'm going to use. Normal to the area surface. And you can extrude upwards and downwards both. So I'm going to extrude only downwards. Say, let's say 12 meters. 12 meters of thickness in the -3 direction. And I'm going to divide it into 12 segments so that each each solid element will be 1 meter in height. And because I use this ground slab, I have to get rid of the ground slab as well. So I'll say delete the source object. So it will extrude it. Now you can see the soil has been created, and go to this level, -12. And I have to say that assign, joint, restraint. I have to say that the soil is supported. The soil is supported. So I have a soil that is supported, and on top of that there's a building. But the problem is, the building is at a wrong height. So I'll bring this height, and it's at a height of 10 meters. So I can replicate it at -10, and I can delete the original object. And that will bring the structure directly on top of the soil. Directly on top of the soil. Now the structure is resting on soil, and if you want to see the real situation, you can say that select properties, area, and raft 1200. Now you can see the raft is actually resting on soil. You can see the raft is resting on soil. Raft is resting on soil. And we can ask it to analyze. Take a little time to analyze. Now you can see the measure period of vibration is slightly higher than earlier. Now it's almost over. Now the analysis is complete. And you can see the deformed shape. And here you can see a deformation of 46 millimeters vertically, 0.466, 0.0466, 46.6 millimeters. And the soil here, still the rough foundation, has deformed less, that is 23 millimeters. And the deformation in this area also 46. Displacement in this area 46, 37, and the displacement here again 46. The displacement of the soil here is about 40 millimeters. Now that is the deformation of the soil. And as you come this way, the deformation of the soil has reduced to 35. And when you are coming this side, it is 35 and so on. And if you look at the vertical deformation of the structure, 46 millimeters. And that is due to the dead weight of the structure. And if you consider a reasonable case where you get dead plus other loads, like service combination 2, which has wind as well. Service combination 2, service combination 2 has wind as well. Doesn't matter, we have a look at it. The service combination. And I look at the deformation. It's about 60 millimeters. When all these loads are acting, it's about 60 millimeters. Here also you get about 45 millimeters. Here you get 60 millimeters. And if you look at the load patterns, it's all dead. Right. So that's the type of deformation you get. And we can also view Z0 and then ask it to display the moments due to combination 4, and you can see the moments. The variation is slightly different now. But some places you get higher moments because soil is weaker now. So because of that, under the columns you get a bigger moment. If you can recall the earlier model on springs, we had something like 900 under the column But here now we are having something like 1500 under the column. Whereas we had moments of something like 500 in this area, now we are having only about 250 hogging, because it sags more, because now the soil is weaker. Now the soil is weaker, and we are expecting a lower bearing capacity and also a lower elastic modulus. Because earlier we consider it's sandy soil and the dense sandy soil, and the bearing capacity is about 150. And generally for a bearing capacity of 150, you get a higher elastic modulus, because sandy soil can give a bearing capacity of 150 when it is fairly strong or dense sand, not loose sand. Loose sand cannot give a bearing capacity in the range of 150, and only a stronger sand, dense sand, can give that kind of bearing capacity. So basically we are having a weaker soil and we are getting these results. And we can also see y equals 0, yes. And we can see the stresses in the solid, and service combination 4. We are getting stresses in the soil around 150, 160 range. But as you go down, it will start increasing, because then the weight of the soil will also start acting. So in this area, you get some dispersion of the stressors, because due to the presence of the raft, there will be a dispersion of stressors. So because of the dispersion, the density contribution will be less. But as you go down, you will see the density of the soil can contribute more, and it increases. So you expect this area, the stressors to be higher, because the weight of the soil will also be contributing. Whereas in these areas, the stressors will be distributing, and here you can see very low stressors in this area, the soil, whereas you can see the raft is actually distributing the loads over a wide area, and because of that reason you are getting slightly lower stressors in this area. And so if you have a bearing capacity of about 150, or can be even less, around 140, a bearing capacity of around 140, you will be okay. And you can see the earlier problem also, with the sandy soil also, we got similar answers. Soil pressure of about 140. This one also we are getting similar answers, but we are getting the variation of the stressors in the soil, and you can see how the soil will distribute the stressors with the height and also laterally. You can see how the soil will disperse the pressures laterally. And in addition to that, any questions on this? Indranil, can you understand the comparison?
Yes.
Right. And then there's another variation that you can get, and that is sometimes, you know, we get local pockets of weak soils, and we can see how it affects. And the important thing is to see how these weak pockets can be modeled. And so we say save as 7, and so let's say, you know, in this area we are having a weak pocket. So what we do is we go to 3D. So let's assume that, you know, in this area we are having some weak pocket. So what we do is on the 3D diagram we can select that particular area. Because it's a massive area that I have selected. And what I do is I'll ask it to show the selection only. And then I will look at it from the plan. And let's say the weak area is under this particular column. So this is the weak area. This is the column location. And there's a weak area in this pocket. So we select this area. Selection only. So that's the only area that we have selected. The column is there, and that's the weak area that we have found where there's a weak pocket that we cannot remove. So we have to live with it because it's too large to remove and compact. So we have decided to go with a rough foundation where we are going to deal with this weak area with the foundation. And we are going to say assign so that is a selected assign solid properties, or it's clay soil now. If you select any of these areas, and we can ask it to display all. So you can see that it's a heavy program, heavy model. And view 2D Z0 and if you look at this area, we have laterite soil, and here you have clay soil. You can see clay soil in this area. Can you see that? This area clay soil and this area laterite soil. So this way you can actually cater for the local pockets, and we can ask it to analyze now. It will take about 1 minute more, complete analysis. And you'll see there's some effect, minor effect on the natural period of vibration, only a very minor effect. Early it was 1.13, now it is 1.15, very minor effect. Display, deformed shape. So you can see there is some deformation due to that weak pocket. So it's 68 here, 72, 72, 69, 69, 71, 71, and if we look at, so it's 0, and display shells in 1 due to combination 4. So in this area you can see greater sagging. So, but raft will be able to withstand because it's having a depth of 1.2 meter. So raft should be able to withstand that. And so you can see the various pockets that you get with weaker soil also can be represented. So there will be some variation in the bending moment diagram, and this way also you see some variation in the stresses. So is that clear?